Okay, the purpose of this video is to show how you can use regression analysis tools in Excel. Right, so the first thing you need to do is activate the data analysis tool pack if you don't currently have it activated. Now, how you can tell, if you look in the data option in the ribbon, you'll have data analysis over here to the right. If you don't have that, the data analysis tool pack does come installed with Excel. You just have to activate it. So to activate it, you'll go to File, right, and then for me, it's under More. Oh wait, let me change my view here because I know I'm going to bring up windows that you wouldn't be able to see otherwise. Okay, so More, and then under Options, this brings this up, right? And you want add-ins, Cell add-ins, go, and then make sure that Analysis Tool Pack is checked here. Click OK, and that should make data analysis appear over here to the right if you're in the data part um, of the ribbon. All right, so having done that, let's get into this and show how regression analysis works. Right, so we have under data analysis a number of options available to us listed in alphabetical order. Regression is what I'm looking for. We're just going to do a simple linear regression here. Right, so I'm going to click OK. And here are my options. So the first thing I want to know what my y range is. So the y is going to be your dependent variable, the one that is going to be explained by whatever your x variable is. Right, so in my case, I want to know whether we can explain the Canton, Ohio unemployment rate based on the US unemployment rate. So I'm going to input my y range as Canton unemployment rate. So click the arrow here so that then I can select. I have this is monthly data, and you can see I have it's quite a bit of data. I think maybe like not quite 30 years of data here, right? Then input my x range. That's where I would select my independent variables, right? Or explanatory variables, those things that I'm using to explain whatever's happening to the dependent variable. Right, so you need our y range, our x range. You can use multiple variables for your x range. That would be multiple linear regression. In our case, though, we're just doing simple linear regression. So we have one x, one y. That makes it simple. If you want to have multiple x's that you're putting into your regression, you do have to have them uh, in adjacent columns in your Excel spreadsheet. Okay, that's just a limitation of this particular tool. Labels, what that means is that I have labels at the top of my columns, and I do, so I'm clicking on that. What constant is 0 does, what linear regression does, it gives you a straight line formula, so that y equals mx plus b. If you tell it that the constant is 0, it will go in and say, oh, well, then we know that the b is 0. Sometimes that would be the case. There are some things where we would know that. This is not one of those, right? So I'm just going to leave that open. Confidence level here, what that is going to do, that allows you to calculate a confidence interval for your coefficients in your linear regression. I'm not going to mess with that here. It will automatically provide me with a 95% confidence interval. If you want something else, then you could put that in here. I don't need to do that. Then, for output options, I can choose, I'm actually going to choose an output range, so it's going to be here in the same spreadsheet. And then if I select, say, D1, then that means my output is going to start in D1 and then go from there down and to the right. I could just put in a new worksheet if I wanted to, or start an entirely new workbook. That's really up to you. I'm not going to select any of these other options, but you can have it report out your residuals. That'd be the errors, and also standardizing those, or also plotting them, plotting how well the line fits, that kind of stuff. The normal probability plot, that tells you how close you are to a normal distribution. I believe it's specifically in your x variables. But I don't need any of that for what I'm doing here. I just want to get the results from a basic, simple linear regression and see what the results look like. Actually, no, I think the normal probability plot might be for residuals. I don't recall. Okay. All right, so anyway, we'll just go ahead and hit OK and get our results. So it takes a second to do the analysis. It's taking longer than I anticipated, actually. And there it is. Okay. Right, so this is giving me my best fit line. So let's go through some of the outputs so you can see what exactly it is reporting. Right, so the first thing we'll see is these regression statistics. So this is just giving you facts about the overall regression. So here, the first thing it gives is what we call multiple R. That by itself doesn't have a whole lot of interpretation. The R squared, though, does. So R squared tells you how much of the variation in your y variable can be explained by the regression. Right? So in our case, it would be 82.5% or so of the variation that we see in the Canton unemployment rate can be explained based on the US unemployment rate. Right? So that's whether that's high or not, it really kind of depends on the case. Generally speaking, the simpler the process is, the higher the R squared you'd expect. Right, so if you are running controlled experiments in a physics lab, you would expect your R squared to be extremely high, so something very close to 1, so like 0.999. That is, there's not a whole lot of random variation from other factors that have an influence. If we're talking about things like social science data, where we're trying to look at things where it's a complex process, and so there's a lot outside the regression that we would expect would have an impact, in that case, an R squared of 0.3 might actually be quite high in some cases. So in this case, we're talking about unemployment rates. It looks like the Canton unemployment rate, 82.5% of the variation in it can be explained from the US unemployment rate alone. I'll let you decide whether that's high or not. The adjusted R square, what that does, that adds in some penalties for the number of explanatory or independent variables you're using. Otherwise, you can increase your R squared just by adding more and more variables to it. As long as those variables aren't perfectly correlated with each other, you're going to get higher and higher R squared. So we need to have some kind of mechanism to take away the incentive to just throw whatever you can right into the regression. The standard error, this gives you some sense of how precise an estimate is going to be based on this particular regression. Coming underneath this, we have the ANOVA, and also the number of observations is here. That's fairly obvious. The ANOVA table, the thing that I would really highlight here is this significance F, which we have here in my column I. Right, so what that is the statistical significance test for the regression. Right, so this would be where we'd typically compare this with the standard value of 0.05. Right, and this has the underlying hypothesis is that there is no connection between your independent variables and your dependent variables. So if you end up rejecting that hypothesis by having a significance f less than 0.05, what that tells you is that there is some kind of connection between your independent variables and your dependent variable. It looks like there's a statistically significant relationship going on here. Now, how important that is, well, that's where you'd come back to the R squared. Because it very well might be, sometimes you'll have a significance f that's very, very low, which means that you would definitely reject the null of no relationship. But at the same time, your R squared might be really low. So, okay, there's definitely a relationship here, but it doesn't explain very much. That is a possibility. We could get that combination. It's also sometimes possible, though I'd say rare, to have a fairly high R squared, but a very low significance f. I think that's a technically possible thing you'd find in really, really weird cases. Usually if you have an extremely small sample, I think is when that would show up. Okay, but for the most part, if you have a very high R squared, you're going to have a significant relationship. Then the last thing to look at would be our coefficient table. Let me adjust some of these widths, just so it's easier to actually read what it says. Okay. All right, I think that's probably clear enough. Right, so the first thing here would be this column of coefficients. So intercept, that would be the b in your y equals mx plus b. And US unemployment rate, this coefficient, that would be the m in the y equals mx plus b. So effectively what we're doing here, put this all into an equation, what we're saying is that the Canton unemployment rate is equal to 0.846 or so, right, plus 1.0389 or so times the US unemployment rate. This is what that relationship would look like, right? So the intercept term, right, coming from the intercept coefficient, and then the slope on your US unemployment rate coming from the US unemployment rate coefficient. Now, so this is the equation you'd use if you want to make a prediction. Now, very important is that what regression provides us with is the average relationship. So this may not necessarily match for every single point. Okay. Another thing to remember is that these coefficients are measured or are estimated, right, with error, and that is what the standard error here does. So the standard error gives you some sense of kind of how much of a margin of error would there be, or what's the basis for that margin of error that we would use, say, for confidence intervals. Speaking of confidence intervals, we have those over here. Right? So this is telling us that if we're doing a 95% confidence interval on that intercept, right, then while our best estimate is 0.3846, that's it. That's our best estimate. At the same time, there's a range around it. So we're 95% confident that this intercept will be between 0.083 and 0.686 or so. Similarly, for the U.S. unemployment rate, right, our best estimate of the slope is 1.0389, but we're 95% confident that it's somewhere between 0.9881 and 0.898 or so. And so we can use that confidence interval to acknowledge that there is a bit of a range around these. One thing that I might use this for in this case is the fact that 1 is inside that confidence interval for the U.S. unemployment rate tells me that if the U.S. unemployment rate goes up by about, let's say, 1 percentage point, we should see Cantons go up by roughly that same amount. Right? So it'll be fairly close together as far as that goes. All right, so that would be another thing. Right, so there would be our confidence intervals for any of our coefficients, whether it be the intercept or the slope terms. The other thing we can do is that there is built into this some hypothesis testing as well, where we have our t-stats, as you would compare those with critical values. Remember, critical values typically around 2 or so. And what this is testing is the hypothesis that this particular coefficient is equal to 0. So when I see there for the intercept, the coefficient, the best estimate is 0.3846. Well, that looks like it's pretty close to 0 maybe, right? So I might think that, well, this is basically 0. Well, that's what the t-stat and the p-value for this line would help me test. So if my null hypothesis is that the intercept is equal to 0, then looking at the actual value of the intercept, the standard error, what we can say is that we are actually 2.5 or so standard errors away from 0, which would give us a p-value of 0.0126 or so. Right, so remember that p-value, we normally would compare it to right about 0.05. So that's a measurement of how consistent we are with that hypothesis. We're under 0.05, which tells us that our estimate isn't actually very close to 0, at least it's not very consistent with that hypothesis. Meanwhile, when you look at the U.S. unemployment rate, this p-value, very important when you interpret these, that 1.2, that E indicates times 10 to the power of whatever follows. So this is 1.2 times 10 to the negative 131st power. So basically we're looking at 0.000 and continue saying 0 for 130 times before you get to something that is not a 0. That's a real small number, really, really close to exactly 0. Right, so that does suggest, along with the t-statistic of over 40, that there is actually some kind of relationship here that would be considered statistically significant. Now, its economic significance, that is, kind of how important is it, that is something where we'd have to think about the coefficient in the context in which we're operating. So is this one-to-one relationship, roughly, is that going to be important in some way? Sometimes you're going to find cases where you have a statistically significant relationship, but the coefficient is just really small, so it doesn't seem like it makes much difference, right? So we need to think about the importance, right, of this relationship in the context in which we are. And that's something where the units will matter. So 1 may not make a difference if I'm talking about, say, the number of inches I'm having to travel or something like that. Traveling an inch, I do that more or less sitting in my chair, just backing away from my desk. On the other hand, 1, if we're talking about an increase in the unemployment rates are normally around 5-6% on average. So a difference of 1 might be significant, right? So you really need to consider the specific units in which you're working to figure out whether or not these numbers are significant in the particular context. Right? So that's just a quick overview of the basic things that you can do for simple linear regression in Excel. I hope this was helpful, and signing off.